You are already familiar with the concept of resistance, which is the difficulty, you could say, of charges flowing freely in a circuit. Well, there's something that is even a little more fundamental, which is the concept of resistivity, which is just the characteristic property of material that causes resistance to arise. All right. So here I have an example, like a conductor, cross-sectional area A and length L. And how does the resistance depend on those physical parameters and what the substance, the material, the conductor itself is made of? Well, we know that resistance is volts over current. That's Ohm's law. That's how many ohms it is. But now, resistance is proportional to length. We have this bar here, make it longer, it's like more series resistance, right? And resistance is proportional to something else. Remember, in the analogy of electricity, I like to use water through a hose. Well, what if the hose is bigger? If it's bigger in diameter, is it easier for charge to flow or harder? That's right, it's easier. If you double the area, it's like having the two doors side by side in a parallel circuit. It makes it easier for the charge to flow. The resistance goes down. So is resistance proportional to area or something else? Did you guess correctly? I hope you didn't answer yes to that question, because it's inversely proportional. As area goes up, resistance goes down. All right, so there's our logic for the material, like a conductor. Now, in the past, we've said conductors have no resistance, but they have a tiny amount of resistance. Unless it's a superconductor, we can't get rid of all of it. So the resistance equals, we jam these proportionalities together and put a constant in front, and the resistance is KL over A. Now, that proportionality constant is what we mean by the resistivity. The symbol is rho, and that is a characteristic property, as I mentioned. All right, so let's do an example. Well, we can just rewrite this as rho L over A. All right, K is rho, so there is it fully expressed. The unit is the ohm meter, and it may seem a little funny, but that makes it consistent. And so here we go. And I'm going to use the example, that's kind of disturbing, I realize, of a gymnast hanging on a high voltage transmission line. I don't know why she's up there in the first place, but who else but a gymnast would be up there hanging from a wire? All right, well, anyway, it doesn't really matter. There's a lot of data here, so let's kind of go through it. Her arms are spanning 1 meter of length. Now, really what's important is what's the voltage across her arms, which is going to result in a dangerous shock. Perhaps. We're going to find out. Now, the resistance of the physical body varies a lot based on sweat and the conductivity is highly variable based on the circumstances. Your hands are wet or sweaty. It's much less than if they're dry, but as a reasonable value, I'm going to say it's 2,000 ohms hand to hand. Now, the cross-sectional area of the wire, this high voltage transmission line, is, and by the way, that high voltage can be upwards of 1,000,000 volts, so it's insanely, it can be crazy high. So 1 square centimeter is the cross-sectional area, and the resistivity, we'll assume this is a copper wire, even though it probably isn't because it's too expensive, but that's that value. A very small, look at that, -8, amount of resistivity because it's a very good conductor. Makes sense? Let's say the current flowing in this wire is 100 amps. Keep in mind, it only takes 1/10 of an amp to stop your heart from beating, and that results in death. Okay, so change in voltage, or the voltage drop, or the voltage across her hands. Now that's the important thing. That is the important thing. But don't be misled to thinking that this 100 amps is flowing through her body. That's not it at all. It's basically flowing through the wire. The question is, what's the voltage drop across her hands? That voltage drop with Ohm's law would result in the current going through her. So that's what we're looking at. The voltage drop, or the change in voltage, is the current times the resistance. But now that current is going through the wire, and we know what it is. It's 100. But the resistance is resistivity L over A. So that's what I just replaced it with. So now it's just a matter of plugging the values in. This thing is going to be really tiny. The length is a meter. The cross-sectional area is a square centimeter. We got to convert to standard units. So here's what it looks like. 100 times this small number over the number of square meters. Okay, it's now -4 square meters, which gives us 17 millivolts. 17 millivolts. If you do Ohm's law and look at the current flowing through her body, with 0.017 volts divided by 2,000, oh my gosh, that's so small. Certainly only in the microamp arena. It's no problem at all. Wouldn't even feel a tickle of the electricity flowing through. Now getting off that high voltage transmission line, that might be a little more tricky. She certainly could drop, but that might be hazardous to one's health because those things can be way, way high up in the air. So she could maybe otherwise hand over hand to where the wire connects to the pole, but don't let go of one hand and swing over and grab the pole with the other hand, because then you've got that 500,000 volts or whatever across you and you're cooked real quick. You'd probably want to drop one hand, and as you're swinging over here, let go of the other hand and then just grab this pole all at once and then climb down. Okay, I'm getting carried away here, but you can envision your own scenario for making sure the gymnast is safe. But hanging onto the wire itself, not a problem.